Question 19. Charged particles, each of mass m and charge q, travel at constant speed in a circle of radius r in a uniform flux B, flux density B. Which expression gives the frequency of rotation of the particles in the beam? Okay, so this is equating the force on a moving particle, which is BQV, to the centripetal force, which is mv squared over r. Right, so let's simplify this a little bit. We got rid of the v there. We can then, what are we trying to find? The frequency. So we need the frequency as part of v there. So we also need that v is equal to r times pi omega, and omega is equal to 2 pi f. So we have bq is equal to m over r, v, which is r omega, times by 2 pi f. So that's omega there. My r's cancel, which is good because there aren't any r's in any of those answers. And we're still after f, aren't we? So we want f is equal to bq divided by 2 pi, and I've forgotten something, I've forgotten my m there, which is A. Okay, question 20. A vertical conducting rod L is moved at constant velocity v through a uniform horizontal field. Right, which of these gives the correct expression? Well, if you move the rod vertically like that, then you're not going to cut any field lines, so therefore you're not going to induce any EMF. So that one's false and that one's false. Right, if you move the rod like that, then you are going to cut field lines. Now you can work this out, but there really is no need. If you just use a bit of common sense, this is saying that if the B field is stronger, that you're going to get more EMF. That seems logical. If the wire is longer, you're going to get more EMF. That seems logical. And if you move it faster, you're going to get more EMF. That seems logical. Whereas this one says that the B field's bigger, then you're going to get more. That seems logical. If the wire is shorter, you're going to get more. So that seems logical. And if the speed is lower, then you're going to get more. That's also illogical. So, because that would mean if you didn't move it, you'd get maximum EMF induced, infinite EMF. So that's clearly false. So it must be this one. So what I'm suggesting there is, with a little bit of deduction, you don't actually need to work out all of the maths. You can do. Question 21. A simple pendulum system and a mass spring system have the same frequency at the surface of the Earth. The pendulum and mass spring are taken in a mine where the acceleration due to gravity is less than that of the surface. What's the change in frequency of the simple pendulum and the change in frequency of the mass spring? Okay, so simple harmonic motion here. So this is a common question. Sometimes you move it to another planet or something like that. The mass spring system stays unchanged. So it's either that one or it's that one. Those two are both out. Okay, now the time period for the simple pendulum is equal to 2 pi root L over G. Flip that upside down and you get the frequency, 1 over 2 pi root G over L. That means that the frequency is directly proportional to the square root of the gravitational field strength. So down the mine shaft, the acceleration due to gravity is less than on the surface. So if this is less than on the surface, then the frequency has decreased. It's that one there. Now this is a little bit weird because the mark scheme says C. I think they have got it wrong. I think it's D. And unless someone convinces me otherwise, then I'm sticking with D. Question 22. Graph shows how flux linkage through a coil changes. So the induced EMF is to do with the rate of change of flux linkage. Okay, so the rate of change is essentially the gradient of this graph. So that's constant there, so you're going to get a constant EMF. There the rate of change is 0, so you're going to get no EMF. So the EMF in the coil is constant, then becomes 0 after this time. So that's C. A liquid flows continuously through a chamber. So we have some sort of tube here and well, a chamber here, I suppose, which has a heater on it. There we go, heater. So heat is pouring in there, delta Q there, containing electric heater. When steady state is reached, the liquid leaving the chamber is a higher temperature than the one going in. Seems reasonable. Which of the following will increase the temperature change with no other changes? Increasing the flow rate of the liquid. That's going to reduce the temperature change, isn't it? Because you've got more liquid, so the heat's spread out over more liquid, so the temperature will be less. Changing the liquid to one with a lower specific heat capacity. That's going to increase the amount of temperature increase of every fixed mass of liquid. So if everything else stays the same, then that will increase the temperature. So it's that one. Just rule out the others. Using a heating element with a higher resistance. Well, let's assume that they've got a constant voltage. The power of the heating element is V squared over R. So a smaller voltage, a higher resistance would reduce the power, therefore reduce the rate at which heat is going in there. Change the liquid to one that has a higher density. That's going to have no impact whatsoever as far as I can see. Right, the temperature of a hot liquid in a container falls at a rate of 2 Kelvin per minute just before it begins to solidify. The temperature remains constant for 20 minutes. So what the idea is here, you've got some liquid here and it's losing heat. And it loses heat such that every minute it loses 2 Kelvin of temperature. And then, once it reaches its freezing point, it continues to lose heat and takes 20 minutes for it to freeze. Right. Okay, so there are various ways you can do this. The way I did it was I thought, well, in 20 minutes, how many degrees Kelvin would it move? Well, if it's 2 degrees Kelvin per minute, then in 20 minutes it would move 40 degrees Kelvin. So it's definitely either going to be that one or that one. It's not going to be either of those two. So we've got 40 degrees Kelvin. So let's think about this. We've got the delta Q is equal to ml, and we have delta Q is equal to mc delta theta. Right, so in 20 minutes, those two values are going to be the same. So we've got ml is equal to mc delta theta. Well, the masses are the same. And you have then, what do we want? We want specific heat capacity of the liquid divided by the latent heat. So we want 1 over delta theta is equal to C over L, which is what that fraction there is. So that's 1 divided by 40, so it's that one. Okay. A fixed mass of gas occupies a volume V. The temperature of the gas increases so that the root mean squared velocity of the molecules is doubled. So we're looking at PV equals nRT. What will be the new volume if the pressure remains constant? So that's constant, that's constant, that's constant. So V is proportional to T. So we just need to know what happens to the temperature. Well, the temperature is directly proportional to the kinetic energy of the molecules. If the root mean square speed of the molecules is doubled, then that means that the mean square speed quadruples times by 4, so the temperature goes up 4 times. So the temperature goes up 4 times, the volume goes up 4 times. So it's that one. 6. This is a hard question. Lots of people will find this difficult. It's difficult to know where to start on a question like this. It's always going to be related to gas laws. So we're going to be ultimately using PV equals nRT, the ideal gas equation. So the first thing to do is to think about what's constant, what changes. Well, you've got the mass of gas in here and the mass of gas in here, when you open this valve, are going to mix together. The volume at the beginning of both of them is the same, and the pressure is going to change. It says that the temperature remains the same. So let's work out what the number of moles of here is and the number of moles here is. So the number of moles in X is going to be, well, it's going to be P times by 2V. And times by another constant as well for all of this other stuff that goes on here. But that's constant, so N is proportional to PV. So Nx is P times by 2V, and Ny is equal to 2P times by V, which is, lo and behold, the same. So that's equal to 2PV, and that's equal to 2PV. Okay, so that's the initial amounts of gas that we have in terms of their pressure and their volume, and R and T as well, but let's just ignore R and T because they're constant. Okay, continuing on then. When you mix them, the new volume is going to equal 3 V's, 3 V1s, if I call these V1s there. The new volume, V new, is equal to the volume of both of these added together. This is negligible here. The new pressure is equal to what we're trying to find, and the new mass is going to equal these two added together. So that's going to be 4 old P times by the old V. Okay, so we use this equation again, and we have new pressure times by new volume is equal to the new mass, which is the 4 times by the old pressure times by the old volume. So new pressure is equal to 4 times by the old pressure times by the old volume divided by the new volume, which is 3 times by the old volume. They cancel. You get 4/3 of the original value, which is C. Okay, so those questions are tricky, but just think about what you can figure out from the beginning. So at the beginning, I can figure out the number of moles in each of these, and then compare new and old, and that's how you do it. And you're always coming back to this. Remember to ignore everything that's constant, because it all just cancel itself out, and only deal with the things which are variable. Okay. 27. A radioactive nuclei emits a beta, then an alpha, then a beta minus. So that is going to increase proton number twice, and that's going to reduce it twice. So the isotope will have the same proton number, so it will be the same element. Well, same element with a different proton number, that's obviously nonsense, because that's the definition of an element, is constant proton number. A new element with a higher proton number, no, it's going to be the same, and a new element with a lower nucleon number, no. Okay. Which of the following best describes the decay constant for a radioisotope? So this is just a book learning question. You need to know it. Reciprocal of the half-life of the radioisotope, not quite, because lambda is equal to ln of 2 over t half, so it's not quite a reciprocal. The rate of the decay of the isotope, nope. The constant of proportionality, which links the half-life to the rate of decay, no. The constant of proportionality, which links the rate of decay to the number of undecayed nuclei. Yes, that's correct, and you can find that on your formula sheet there. So it's D. Question 29, which of the following is equal to this ratio here? So we're looking at this equation here. So we need the cube root of each of these. Cube root of, we're only interested in the nucleon numbers. Cube root of 125 is 5. Cube root of 64 is 4. So it's 5 divided by 4, which is that one there. After 64 days, the half-life goes to 1/16 of its original value. Okay, so we start off with 1. We go after 1 half-life to a half. After 2 half-lives, we go to a quarter. After 3 half-lives, we go to an eighth. And after 4 half-lives, we go to a 16th. So that's 1, 2, 3, 4 half-lives. So each of those has to be 16 days, 16 days, 16 days, 16 days to add up to 64. So it's that one. Finally, question 31. The graph shows the binding energy per nucleon as it varies for stable nuclei. So what's the approximate binding energy of W? Is that tungsten? I think 184. Ask a chemist. So 184 is what, about there-ish? So it's something along there. So I'm going to say that's what, 7.5. So the binding energy will be 7.5. What are the units here? Mega electron volts. So times 10 to the 6 to turn it into megas, times by 1.6 times 10 to the minus 19 to turn it into joules. And then that's per nucleon, so we need to times by 184. So here goes 7.5 times 10 to the power 6 times by 1.6 times 10 to the power minus 19 times by 184 gives us, right, we want it in petajoules, so press ENG button and it'll take us to times 10 to the minus 12, so it's 220, so this is the closest here. Why have I got a different answer? Well, if you drew that line slightly differently, used a slightly different value there, you get that, but you're not going to be out by that much, are you? So that's where that comes from. Okay, and that is the end of that paper. So I hope you found that video useful. If you did, please like it, post comments, and for everybody that's listening, good luck in your exams.